with the computational mesh, and we require y plus value approximately close to 1. Okay. And sometimes it can be used along with valve functions also. There is no harm in that. So in those scenarios, we will not. So we can go for a slightly higher y plus around 10 or 15, and then the valve functions we capture the near valve phenomenon with we bridge with the log-low region. And this model is actually best suited for internal flows and flows that exhibit strong curvature, etc. So best example for this model is like flow through a pipe bend. So those are the applications where we can use K omega model. So in this model, one factor which we need to take care is like our mesh should be very denser to the wall. So our y plus should be close to 1. Accordingly, we need to place the first cell height. So those concepts we will discuss when we go for y plus discussion. And this is another famous model, SST K omega model, shear stress transport K omega model. So this is actually a combination of the first two models we have seen, that is K-Epsilon and K omega. And here also we require y plus up close to 1. But here one advantage with this model is it automatically switches between K omega and K epsilon. So in the near wall where the velocities are less, the model switches to K omega and it works. And in the free stream or away from the wall where the flow velocity increases or the turbulence increases, it switches to K epsilon. So this is actually a very good model for a prediction of flow separation and reattachment. And denser mesh is required near the wall and free stream. And this model is well suited for the problems like in the pump, centrifugal pumps, or even external aerodynamics. There are some, with some modifications, this model can be used. So these are the applications of SST K omega model. So these three are the common, most common used turbulence model. There are some other models also, but I'm just touching upon the most commonly used turbulence model. Yeah, there are other two approaches of turbulence modeling. And so till now what we have seen is RANS approach, Reynolds average and Navier-Stokes equation, where we are actually interested in the average quantity. So we average the Reynolds Navier-Stokes equation, and we using the turbulence model we find the Reynolds stresses. Now the another method is direct numerical solution, or it is famously called DNS. Here actually there is no averaging, nothing. This fluctuating components directly we plug into Navier-Stokes equation, and we try to resolve all the eddies with mesh, be it a large eddy, be it a small eddy. We try to resolve all the problem. We try to resolve the domain with the computational mesh. Then we need to go very finer mesh near the wall to capture the smaller eddies in the near the wall, and it becomes computationally very much intensive, and it is computationally very much expensive. So it is not suitable for industrial applications. Okay, for academic interest, one can actually explore, but yeah, so that is what this direct numerical simulations. And another one is large eddy simulations, where it is a kind of industrial plus academic, but still it requires a lot of computational power. So in LES simulations, we resolve some of the eddies with a mesh. So you can see two pictures here. One is written here bad LES, and one is written here good LES. So what is the difference? You can see the left side we have a bigger eddy. Then moving towards right, we have smaller eddy. Then moving towards right, we have very smaller eddies. But if you see the good LES, yeah, our area under the curve actually extending towards more smaller eddies. So this is a good LES. But the top one, it is just stopping here. So it is only capturing the eddies with this size. But here it is furthermore capturing eddies with smaller size. So this is always there is a trade-off between the computational power we have and what we need to capture. So accordingly, one has to decide what is the size of cutoff size of the eddies they need to resolve. And there are some other mathematical models also. So that is beyond the scope of this, how they can specify the cutoff size for large eddy simulations. Okay, so these are the overall brief about the turbulence modeling. So now coming to the y plus. So I told like for K epsilon we need y plus between 30 and 300. K omega it should be close to 1. So what is this y plus? So this is a non-dimensional wall distance which is used to place the first layer near the wall. So using the y plus, we will calculate the first layer of mesh where has to be placed in our problem. Okay, at what distance from the wall. So suppose if you are using a turbulence model, K-Epsilon, and we know that y plus should be between 30 and 300. So we are going to do meshing. We need to calculate our first layer height. So we could actually put in y plus, we know 30, and y is what we need to calculate, the absolute distance from the wall. And mu tau is the frictional velocities, which is given by the square root of a wall shear stress by density of the fluid. So in most scenarios, we will not be knowing the actual wall shear stress. Okay, but for say simple problems, say flow over a flat plate and all, we know the formula for wall shear stress. It is CF by half rho u square, and CF is given by some empirical correlation 0.0064 root of REX or something. So in those scenarios, we can actually calculate the wall shear stress and density. We know density of the fluid, and you can actually find the first cell height, absolute distance from the wall, and based accordingly you can grow your prism layers and put the first cell height, and then accordingly you can grow how many layers you want. So that is one way of doing it. Suppose if you are not able to calculate the wall shear stress, suppose if you are, say this is your geometry and you want to put first layer height, so then you don't know the wall shear stress, but still we can either go with the flat plate approximation, initial guess, calculate the wall shear stress and calculate the y plus value, by distance, absolute distance from the wall, then grow the prism layers, run the simulation. After the simulation, go and plot y plus, cross check your y plus is between 30 and 300. Make sure, okay, if not, suppose if it is going below some areas where it is coming to 1 or 2, or some areas it is going above 300, then rework on the mesh on those areas, then again run the simulation, and you can correct the y plus. So that is the significance of y plus. So it gives an idea of placing the first layer height based on the turbulence model you are going to use it. Okay. Yeah. Now we will come to the application part of advanced CFD or CFD. It becomes advanced as and we progress towards the complex problems. So here, suppose if you take, so mainly I'm concentrating on 3 domains. There are n number of domains where the CFD finds application, but I am restricting myself to automotive, aerospace, and biomedical. Okay, there are oil and gas, or then other areas like heating and ventilation, turbo machineries. A lot of areas are there, but just I'm restricting to these. Yeah. So in automotive, like the applications are like first and foremost is like the drag and lift predictions of the vehicle you are designing, be it a truck or be it a car, bus, whatever it may be. So that is first application. And second is the underhood and underbody thermal management of a car, bus, or truck. So you have a lot of plastic components and rubber hoses on your engine bay, and sensors, etc., and on the underbody also. Then you have hot parts running on your placed on your underhood and underbay, like exhaust system, manifold, engine, and there is all the neighboring components have a risk of catching fire at certain vehicle operating conditions. Then so you need to simulate it. You need to find the temperature or maximum temperature each component experience in the vehicle. If it is going beyond its design temperature, you need to work on how to protect it. Another is cooling airflow. So you all might have seen certain openings on the front of the car. So those are the openings provide to cool the heat rejected by the engine through the radiator into the engine bay. So those heat will be carried out by this airflow. So one may have to work on optimizing the airflow requirements based on the heat rejections. Another is, as you can see here, like this is a cabin, inside cabin of a car. We switch on the AC, we get nice cool air. But CFD engineer who is working on this problem, he has to make sure that, okay, the moment I switch on AC or the moment the passenger switch on the AC, the cabin has to be cooled within a fraction of seconds, 1 second, 2 seconds. So that he has to make sure. Okay, the air reaches all the passengers, be it in the front row, second row, third row, with sufficient velocity. So then, so all those things he has to take care. The CFD engineer who is working on the cabin airflow. Then obviously this air comes through a duct, so and it is blown by a blower. So he has to optimize the pressure drop in the duct so that he can improve his blower performance. Then obviously there is a vent through which the air expands to the cabin. So the vent shape also he has to design so that the vent makes sure the air to flow maximum expanded to all directions. So those are some critical areas wherein a CFD engineer working in automotive application has to think on and focus. And there are other like air intake system and exhaust system. Those are system level components wherein one have to work for the air intake system pressure drop optimization or flow uniformity index, or exhaust system temperature predictions due to hot gases flowing inside through it. So these are the applications related to automotive. Now coming to aerospace, again, it is a vast field. It is not just limited to what I put 5 or 10 applications on my slide, and it is not as simple as no. Even the other one is also not simple. Yeah. So these are very complex applications where the prediction of drag and lift, again the cabin comfort inside the aircraft, airflow inside the aircraft cabin for the passenger comfort, aerofoil designs, that is the most crucial part of it, the lift and stall, all those aspects. Then another aspect is supersonic missiles. Missiles, because countries make missiles, and what is their main objective is maximum range. It has to travel 5,000, 10,000, or it has to reach 2-3 countries beyond. If they are able to hit, they will be happy. So that range. So again, that also CFD has to play a major role in that. And hypersonic launch vehicles, as you know, like the space vehicles, re-entry vehicles. Actually, that is a very complex phenomenon where you will have this. I'll just mention how complex it is. Like, so it is actually a compressible flow. Then you will have a shock layer at the front of the space vehicle. Then there is a boundary layer, and this boundary layer is a bigger boundary layer than incompressible flow boundary layer. And there is a phenomenon called boundary layer heating take place, which is not there in the incompressible flow. And there is an interaction between the shock which is formed in front of the launch vehicle and this boundary layer that will create a altogether different form of physics, and the vehicle will experience different atmospheric conditions as it travels from Earth to space. Some regions the vehicle will experience the ionization of gases, some regions it will be like inert gases. So then now you can imagine somebody is doing the CFD analysis of this, how much physics they need to solve. They need to solve the ionization problem in the atmosphere, they need to solve the shock problem, they need to solve for the boundary layer heating and prediction, and the interaction between shock wave and boundary layer. So that is a very complex things. Again, the propulsion system design, again these fans and propellers, then the gas turbine and the noise of these fans and propellers, flow induced noise. So all these are the applications of aerospace. Now, so another area of application is biomedical devices. So you might have heard, I don't know, in your curriculum, you might not be studying about all this. You might have heard a lot about automotive and aerospace, but there are medical devices which will save the human lives. Say suppose the human heart is not working. There is a device called blood pump, which can actually substitute for the heart. Then there are stents, there are heart valves, artificial heart valves. Suppose somebody's heart valve is not working, there are heart valves which can be implanted. So though all the design and development of these applications, a lot of CFD is involved. Again, here the complication is we say in automotive application we have seen one version of air, that is incompressible form of air, and in aerospace we have seen another form of air which is a compressible part of air. But here the fluid is blood, and blood is actually a suspension of white blood cells, red blood cells, all those mixtures. And that creates a very big challenge for the design of these kind of devices. So those are the applications, and prediction of aneurysms. So somebody will have a cerebral aneurysm. Also, aneurysm is nothing but suppose we have a blood vessel, and over a period of time there will be a bulging, as you can see in this figure. This is the straight blood vessel, but due to certain chronic conditions or as age progress, this straight blood vessel become like this bulge, and once it start bulging, at any point it can break, and it can mortality can happen to that particular person. So there are models using CFD. One can predict these aneurysms, and suppose if there is an aneurysm, people put stent over there, as you can see there. But then where to put the stent, how the stent has to be designed, and what is the shear force coming in that, what is the flow circulation in that area. For all this, we have to do a lot of CFD based optimization. So these are some of the application part of it. Okay. So we have seen applications, we have seen little bit of theory, turbulence modeling, etc., etc. Having said all this, usually the commercial softwares have made the life of CFD engineer very easy. So once we have a software, we don't have to think much. Everything is there in the GUI. We just need to know what options want, click it, execute it. So as I mentioned before, our workflow is pre-processing, solver setup, and post-processing. Not all the softwares are listed here. These are the few commonly and most commonly and famous softwares which is used in the industry. Pre-processing, ANSA, Hypermesh, Power Delta, ANSYS Meshing, ICM CFD, and solver, ANSYS Fluent, SAS CCM+, AcroSolve, PowerFlow, XFlow, and post-processing, Power Insight, CFD Post, and ANSYS Insight. Yeah, and challenges. Yeah, already I have mentioned in some of the slides the challenges for a CFD process and CFD engineer. So I will repeat it. So we always make assumptions and approximations in order to simplify the problem. That is the biggest challenge for us, because we need to know how much we have to assume and how much we have to approximate. So that is a judgment based on your problem, your experience, and the type of results you want. So that is always a challenge. And always you need to have a really good mesh to capture the complex flow features. And sometimes it leads to the limitations on your computational capability you have. So then you need to take a call what accuracy you need based on your computational capability or computational HPCs you have. Yeah, and sometimes nowadays a lot of aberrations are coming, different turbulence model, different valve functions, different numerical schemes. So then you may be finding, you might be trying to solve a complex phenomenon, and you might be using some complex schemes. Then you will end up with a convergence issue. Then you may need to fine tune the model and get it right. So choosing those parameters, those are also certain aspects of challenges. Then turbulence, as I said, it can always be modeled with approximations. So it is not going to be always 100% we are going to capture the turbulence. So that is also a challenge. Then, okay, computational power, as we already discussed. And the most important is the CFD results are always need to be validated with experimental flow visualization results, and you need to quantify the error which you are having with your experiments. So that is important thing. Yeah, now this is, I think, final slide. Job opportunities. So just don't go with the slide. I have put only very few numbers, and just automotive and aerospace and some engineering service companies, but there are lot of applications, even drug delivery to the or drug mixing, or as I said, the surgical planning. Those are n number of applications, but these are the common, those are specialized things. But the common a CFD analyst or engineer can find job like in automotive, aerospace, and the engineering service companies, like these famous companies I have put, like TCS, HCL, Infosys, Satyam, Minjo, Tata Elxsi, all have CFD teams, and they all undertake projects which we have come across in our previous slides. And if you see the OEMs, Tata Motors, Mahindra, Valeo, Dassault System, Boeing, Airbus, Post Motors, Ford, still a lot of companies are there. yeah, then new startups, like there are nowadays lot of new startups are coming up for electric vehicle development, electric helicopter, a lot of things are coming. So there also find lot of opportunities. And obviously, like in the premier institutions like IITs and IAC or other various government laboratories, you will find CFD research applications, where you will not be doing with sometimes commercial solvers, but you will be working on certain development of certain schemes, or certain turbulence model expansion, or some certain validation of certain problems, or certain solver developments, or addition to the server developments. Those are where you will find the research opportunities also. And I think yeah, by this I'm ending. The presentation is over, and thank you for listening. And I don't know how much time I have took. Hope I have done it in the as per the schedule. Yeah, thank you.